during our conversation about insulting the French, I was partly the time I was using to write down some of the antiderivatives that we've got. My goal today is to finish finding antiderivatives. So it's really a matter of just as many examples as we can. As I come across guys that I haven't done or forgot to write down, I'll add them to this list here. I had a list last time, but I threw it away by accident. So I'm kind of doing a brand new one. So if I recollect last time, we looked at questions where you had to do a little bit of extra math to it before you could find the antiderivative, capital F of x. So let me kind of do that as my start. So suppose you had x squared minus 2x plus 1, and it was going to be over x squared, right? That's essentially question 9. You can't find an antiderivative of this expression. It's just not written as one of these guys. So one way to tackle this would be to call this x to the power of -2 and then distribute it. And if you did that, you'd get an x, you get a -2x to the -1, and you would get an x to -2. And this guy in the middle, whenever you see an x to -1, you have to do that to it. But leave the others alone. And the reason why you have to do that to it is because the antiderivative of 1 over x is the natural log of x. And I'll do a plus c. So, power rule for this guy. Add 1 to the power and divide by the new power. This guy is a log, so -2 logs. This guy is a power rule, right? As long as it's x to the power of anything, and the only exception to that is x to the -1, anything else will work. You can do the power rule, which is add 1 to the power and divide by the new power. And then remember to finish with the plus c and a little bit of style points. Rewrite that as -1 over x plus c. And we are finished. That is the antiderivative of this function. Does that kind of remind you what we sort of did last time? Right. So let's move on to a trig one. There we go. An example of that would be question 10. The function that we're down it in space, there we go. F of theta is 7 sine of theta. Take away 3 secant theta tan theta. And they have a little thing over here saying on the interval. Don't even worry about that. It's just to keep everything mathematically correct. That's all it means. Right, now, antiderivative. I've got a sine, I've got a cosine, I've got a secant squared. If you want to find the antiderivative of them, here's your answer. I don't have yet, so I'm going to add it in, a secant tan. Anybody want to have a guess at what the antiderivative of secant tan is? So you got to say, what function do I need here that its derivative is that guy? So what function goes here whose derivative is that guy? That's a way of thinking of an antiderivative.
An x?
I think I heard it, secant x. You're right, it is. So 7 sine thetas becomes -7 cosine thetas. -3 secant tans becomes -3 secants. And then you add a c. Aren't finding antiderivatives quite, you memorize what things are and then you apply this table to the situation, right? And if it's a multiple like 7, you just stick a 7 in the front. If it's a multiple like 3, you stick a 3 in the front, right? And remember your plus C's. This one looks like this. I'm not going to do anything to that guy. He might look weird, but he's actually not that bad. On the other hand, this horrible 5th root of x to the 4, that's no use to me if I want to find antiderivatives. I need to turn it into a fractional power of x. You would have to do that if you wanted to differentiate as well. What is this guy? What fractional power of x is this guy?
X to the 4/5.
Nailed it, right? That guy goes in the bottom, the power goes in the top. Now I am ready to do the antiderivative. Add 1 to the power. 4/5 add 1 gets you 9/5. Divide by the new power is the same as multiplying by 5/9. So the antiderivative, add 1 to the power, divide by the new power. This guy is going to go over here on my list. That one's a pretty rare one. I'd be really impressed if somebody could tell me it. What is the antiderivative of 1 over 1 plus x squared? Any ideas? Okay, I'll give you a clue. It's an inverse trig function. Inverse sine, inverse cosine, or inverse tan. Last chance. Okay, here goes. It's an inverse tan. So 8 over them just gets you a multiple of them. 8 inverse tans. Okay, while I'm at that, let's put the other guys in. If you ever have to find the antiderivative of that weird looking fraction, the answer is it's the inverse sine. And if you have to do the antiderivative of that one, which is almost identical except as a negative, the answer is the inverse cosine. So here are the 3 inverse trig functions. I may have to write slow if we come up with any more of these fellas. So here is question 12. Function is g of v this time. And it's 8 cosines of v, take away 4 over the square root of 1 take away v squared. Okay. What is the antiderivative of 8 cosines?
Eight sines.
Agreed. Forget about the 4. Actually, forget about the negative as well. Just think of it as 1 over the square root of 1 minus v squared. What is the antiderivative of this guy? It's over here somewhere. What's the antiderivative of this guy?
The inverse cosine?
Okay, if you want to do an inverse cosine, which I'm totally okay with, it would be that one. If you want to do an inverse sine, it would be that. And the reason why you can get 2 answers is, if you want to call it plus, won't you use this? If you want to call it minus, you use this. If the thing's already got a negative, that's factored in here or here. Both of these are correct. According to WebAssign, they wanted the bottom one, but I think the top one is equally correct, so I wouldn't fault you at all for doing that one. How are we doing? We're good? Right. So imagine I gave you the same kind of question, like find the antiderivative thing, right? But I gave you some more information. So 2e to the x, take away 8x, right? So this is going to be what, question 13. So here's the function, and you're being asked to find the antiderivative. Well, that guy gets you 2e to the x, and if you do the power rule, right, you add 1 to the power, and you divide by the new power, and then you put a plus c. Wouldn't that just what we've been doing all day for the last 2 days, right? But suppose I give you an extra piece of information, and I tell you that f of 0 equals 10. So I tell you that the value of the antiderivative function, that's this guy, when x is 0 is the number 10. You can use that to figure out who c is. So that's the new question. Find the antiderivative and find out what number c is, so that when you're finished, you'll have nothing but numbers and expressions, right? Give you some names. This piece of information here, in this case, the capital F of 0 at 0 is 10. This is called a boundary condition. And in some books, it's called an initial condition. Well, let's see how I would use it. I know f of 0 is 2e to the 0. Take away 4 lots of 0 squared plus c. And I also know that it's equal to 10. Does that make sense? Find the value of the function at 0 and make it equal 10. E to the 0 is 1, so that's 2. Take away nothing, still nothing. So 2 add c equals 10. That means that c has to be 8. Agreed? And so the final answer, the one that you would write down in WebAssign, would be 2e to the x, take away 4x squared, but no plus c anymore, now plus a. Would you agree that's just a little extra bit added on to finding an antiderivative? Find the antiderivative and then find out who c is by using this extra piece of information and this boundary condition that they gave us.
Does the boundary condition always define C?
The boundary condition will tell you how to get C. Yeah, its job is to help you find C.
Okay.
So let's try another one of these boundary condition type questions. Oh, this one's good because of the way it's written. It's hard to skip a question because every one is kind of different. So you want to try and see as many situations as you can. And that's the guy. They do have a boundary condition. I'm not going to do that yet. We'll do that right after I finish this bit, and I'll put the boundary condition up here. But it's just distracting if I write it down right now. I look at this question and I'm saying, look, I need antiderivatives. But that guy ain't in this list. So that's a key that there's something not right. Normally that means it's not written in the way that it needs to be written to look like one of these guys. Would you agree that that is him? Right? That negative one is. Now, when I look at him, do I say, oh, I can see, yeah, there you are. You see him now? He's in my list. See him there? He's in my list. So the antiderivative, capital F of x. What does the number 7 get you? What's the antiderivative of the number 7?
7x.
0.
Not 7x. Differentiate it at 0. Antiderivative it at 7x. Okay. Would you agree this guy is inverse tans of x plus my c? And actually, that's the way you should do these questions, right? Find this first. Now, I'll tell you what the boundary condition was. Capital F of 1 was equal to 0. So there's the boundary condition. So now I'm going to use it. F of 1 is 7 times 1, take away 3 times the inverse tan of 1 plus c, and that should equal, in this case, 0. And that's 7. Okay, this is going to get your cobwebs going. In trig, you would be able to find, so it's a good idea to have a unit circle around. What is the inverse tan of 1? In other words, what angle gives you a tangent equal to 1?
Pi over 4.
Correct. So this is 3 lots of pi over 4 plus c. And that makes, I'll put it over here. If you take 7 away from both sides and add that guy, you now know c. It's not a very pretty answer, right? But it's a number, right? It is a value. So our final answer is 7x, take away 3 inverse tan of x, plus c. We're finished. So find the inverse tan with the plus c, use the boundary condition information to find out what c is, and then replace that c by whatever you found out its value was. The next bunch of things we're going to do is that we're going to use multiple antiderivatives. And we're going to have to change our notation to suit that. So if I tell you that f dashed x was x squared plus 6x, take away e to the x, right? Just for example. And I asked you to find f of x, wouldn't that be find the antiderivative? Would you agree? If I tell you what the derivative is and I ask you to find the original. So do you see in this notation, they give you this guy and they ask you to find the original function. And that process going from here to here is finding an antiderivative. The questions that we've been doing before that look something like this. They gave you a function and they called it f of x, and they asked you to find capital F of x. And that was also, that process was called finding an antiderivative. Are we good with that? So it's not that I'm telling you to do something else. Aren't I just giving you notation that looks a bit weird? Right? Well, let's see what the answer is. Antiderivative. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. My friend e to the x, there you go, plus c. Yeah, that was easy. Great. So what was a multiple derivative look like? Well, suppose I told you that the second derivative of a function was 2e to the x plus 1/3 x squared take away 4x plus 2. There, good example. And you're being asked to find the original f of x. So essentially, don't you have to do the antiderivative process twice? Right? So if you do it once, well, won't the antiderivative of a second derivative give you a first derivative? Does that make sense if you undo it once? Antiderivative, you get that guy? Add 1 to the power and divide by the new power. That's a 9th. Add 1 to the power, divide by the new power. And the 2 gets me 2x, and it's a plus c. Are we good so far? Right? Antiderivative, antiderivative. Now, there's a little kicker in the tail here. If you want to find f of x, don't you now need to take this guy and find his antiderivative, right? You kind of do it twice. Well, that guy is pretty boring. Plus, I very rarely ever make mistakes, right? The antiderivative of 2e to the x is still 2e to the x. This guy here, you add 1 to the power and divide by the new power. You've now got 1/36. This guy, you add 1 to the power and you divide by the new power. So you've got negative 2/3 x cubed. What would you get if you did the antiderivative of 2x? What would that get you?
X squared.
Agreed. Now we have a problem. There's a plus c here, right? That's called an arbitrary constant, right? It's an unknown number. It could be +5, could be plus a billion, right? We don't know what it is, but it's there, right? It does exist. What is the antiderivative of plus c? Think of plus c as plus a number. What is the antiderivative of it?
C to the n plus 1 over n plus 1.
Trying too hard. Do something simpler than that.
Is it just CX?
Yeah, just cx, right? Wouldn't 5 get you 5x, 2 gets you 2x, wouldn't c get you cx? Do you see how that adding 1 to power divide by the new power thing, really, you don't need to do anything as bad as that, right?
Is it the same x that's in the rest of the equation?
Yes, same x. X is the variable. So when you do antiderivative, anytime a variable appears, it's going to be in terms of an x. In this case, the number c becomes cx. Wait a minute, there's something missing. Shouldn't you get an arbitrary constant? So what do? You add in a new layer. Do you see in this case, you now got plus cx plus d. Do you see you've got two different unknown constants? Let's try that one again. Let's suppose I did second derivative 3 sine x plus 8 x cubed. Right. Just do that one. And the question was, find g of x. First antiderivative. If you do the antiderivative of a sine, you get a negative cosine. So that's negative 3 cosine x. In this one, you add 1 to the power and then divide by the new power. And then plus c. Are we cool with that one? Antiderivative, antiderivative plus c. Now the one that looks like it's causing more trouble. Now take this and take its antiderivative. Well, if you do a cosine, you get a sine. So negative 3 cosines get you negative 3 sines. If you do the power rule, you add 1 to the power and then you divide by the new power. So that's where the 2/5 came from. What will be the antiderivative of plus c?
CX.
And how are we going to finish this one?
Add D.
do you notice that the end's the same every time? Right? It doesn't matter what the original question is. Aren't you going to finish with a plus C that turns into a CX plus D, right? That's kind of, so is that a little bit cleaner now that you've seen two of them, where it was a little bit, I'm not sure, right? Let's pick one from here then. This one is a version of, trying to find the question now, question 20. And we have a function. Its second derivative is 8x cubed plus 5. Well, if I find the antiderivative, I add 1 to the power and divide by the new power. And I just screwed that up, that's 2. Try that again. Add 1 to the power, divide by the new power. What will the number 5 get me when I take its antiderivative? What will the 5 become?
5x.
5x.
Great. And then won't we do plus C? And now if we find the antiderivative of this, power rule, add 1 to the power, divide by the new power rule a second time, add 1 to the power, divide by the new power. Hopefully this question is getting boring now. What does the plus C become?
C times x.
Plus
T plus
D. We good? Yeah. Let's do a trig one. A third derivative. And the variable is going to be called theta. Not that's a big deal. And this is going to be the sine of theta plus the cosine of theta. If you do an antiderivative, then the third derivative will become a second. A sine gives me a negative cosine of theta. A cosine has an antiderivative of a sine plus a c. If I now find the antiderivative of a second derivative, I get a first derivative, a negative cosine, right? Well, if a cosine gets you a sine, a negative cosine will get you a negative sine. A sine, its antiderivative gets you a negative cosine. What will the plus c get us? What will the plus c?
Cx.
Will it be x this time? Because you're kind of right, but not the right letter.
Oh, C theta.
Right. C theta plus
E.
c. Of course, we have one more to do. A negative sign. Well, a sine gets you a negative cosine, so a negative sign would get you the negative of that, so you end up back with a positive cosine. A negative cosine, well, if a cosine gets you this, a negative cosine gets you a negative sine. Oh. I need to do an antiderivative of this guy, an antiderivative of that guy, don't I? Okay, I'll do the easy one. D gets you d theta, and then you need another letter, so I'm going to call it E. What will the antiderivative of c theta get you? That's the one that's going to hurt your head. The antiderivative of c theta.
It's C over 2 theta squared.
Well done. Don't you add 1 to the power and divide by the new power? Now, I'm going to return back to question 20, because question 20 had an extra piece to it. You were told that f of 1 was 7, and then f dashed of 1 was 3. So there is your boundary conditions. Which means that shouldn't I be able to use this information to figure out C and D? Great. So if you tell me that f dashed of 1 is 3, and I'll write down what f dashed of x looks like. It was 2x to the 4 plus 5x add c. And f dashed of 1 was equal to 3. So 2 lots of 1 to the power of 4 plus 5 lots of 1 add c. 2 add 5 add c is 3. 7 add c is 3. So that makes c -4. Which means that I now know that f dashed of x is equal to 2x to the 4 plus 5x minus 4. I also know that f of x is 2/5 x to the 5, 5 over 2x squared. But instead of cx, I can now write down cx as -4x plus d. Can you see where this is going? I now am going to use the fact that f of 1 is 3. So 2 lots of 2/5, 1 to the 5. 5 halves, 1 squared. Take away 4 times 1 plus d, right, that whole thing, is going to equal 7. Really messy. 2/5, 5 halves, take away 4 plus d is going to equal 7. Time for calculators. If I do 2/5, add 5 halves, subtract 4, and then I do make me a fraction, I get -11/10 plus d equals 7. If I add that to both sides, I get, well, essentially that, but nobody would ever write it like that. I get 81/10, which means that this answer here is 2/5 x to the 5 plus 5 halves x squared minus 4x plus 81/10. So not only do we find antiderivatives or multiple antiderivatives, don't we also find the values of C and D, provided they give me a boundary condition to work with. Are we still good? Okay. What's left? Well, not much. Pretty much on schedule. Here's an application of antiderivatives being used. Suppose I know the velocity of a moving object at any given time t is given by this formula. And I tell you the position of the object at the 4-second mark is 7. Our job is to find the position function. First thing I'm going to do before I tackle that question is to rewrite it as a fractional power. Going to do that. Now, what do you get? Be careful here. What do you get if you do the antiderivative of a velocity function? do you get an acceleration or do you get a position? Do you get A of t or do you get S of t? Do you see there's two sides of a coin here? What do you get if you find the antiderivative of a velocity function?
Position function.
You do. What do you get if you differentiate a velocity function? Different question.
Acceleration.
So you see there's a little going up a hill, down a hill like it's ladder, right? As you go up the hill, well, if I do it this way, if you go up the hill, isn't that differentiation? Right, if you go from here to here, you differentiate. From here to here, you differentiate. So going up the ladder is differentiation. Isn't going down the ladder finding antiderivatives? You see how they work in an opposite direction, but they do similar things, right? You move from one to the other. So add 1 to the power, divide by the new power. Add 1 to the power. Dividing by 3/2 is the same as multiplying by 2/3. If you multiply this thing by 2/3, it ends up coming out like that, plus C. I'm now going to call that this fella, and I'm going to call that that guy. So I'm going to make style points. And I have a boundary condition. And that guy's job will be to help me get this guy here. So what do I know? I know that S of 4 is 1/3 times 4 cubed. Take away 2 lots of the square root of 4 cubed plus C, and we're told that that has to equal 7. For God in Himmel, 64/3. Probably do that in the calculator. Hopefully it comes out nice. I'm pretty sure it does actually. 2 times the square root of 4 cubed, which is 64. Of course, it comes out nice. You get 16. I'll do this on the calculator then. 64 divided by 3, subtract 16, and then make it a fraction because we want exact values. And we get 16/3. So that makes C, well, if you subtract 16/3 from both sides, that's what C is. And that's 21, take away 16, the answer is 5/3. So we now have the position function. It's 1/3 t cubed. Take away, I'll use this version. Take away 2 cube root, the square root of the cube, plus 5/3. So what that tells me is that if I know the velocity of a moving object at any given time, and I know where it is, just one place, right? At the 4-second mark, it's 7 meters away from me, right? If I know that boundary condition, don't I now know where that object is at any given time? It's kind of interesting that you'd be able to get that kind of information by just doing this. So we have one last one to do. Kind of the ultimate version of this. This is question 23. But question 24 is very similar. So we have the acceleration of an object at any given time t is 2t plus 5. And we're told its position at time 0 is 4 meters away from me. And its velocity at time 0 is -5. So if I do the antiderivative of acceleration, I get velocity. Power rule, add 1 to power, divide by the new power. 5 gets you 5t plus c. I'm going to use this piece of information to get c. So the velocity at 0 is 0 squared plus 5 times 0 add c, and that has to be -5, and that's an easy one to do. The answer is -5. So I now know everything you need to know about the velocity. It's t squared, it's 5t minus 5. I can now do antiderivative and get the position. Power rule, add 1 to the power, divide by new power. Power rule again, add 1 to the power, divide by the new power. The number -5 gets me -5t. Add, well, I might as well just call it c again. Right? Just a placeholder, right? If you don't like that, call it d, don't matter. It's going to turn into a number in a minute anyway. I'm now going to use the fact that the position at time 0 is 4. So f sub 0 is 1/3 that guy, 5/2 that guy, take away 5 times that guy, add c, and that should equal 4. And guess what? It's very easy to do. So now I know where this object is at any given time. It's that guy plus that guy minus 5t plus 4. What that tells me in physics is that if I know just the acceleration of an object, right, that's just basically how's its velocity changing through time, right? And I know its velocity at one point, and I know its position at one point. Don't I now know where it is at every point? So the information about a moving object is essentially contained inside its acceleration. How it accelerates is going to tell you, if you get enough boundary points, what it's going to be, where it's going to be. Not only that, don't you also know what its velocity is at any given time as well? That is the power of calculus. Before Sir Isaac Newton, Leibniz was the other guy, but I believe Newton should have got all the credit. Before he discovered or created calculus, this type of question here would have been beyond the math of the time. People didn't know how to work that kind of problem, right? Okay, I know what its velocity is, but how can I use that to figure out where it is? You see that? Even if I know where it is, one point wasn't much help to them. You see, they couldn't really figure it out very easily. And now calculus came along and boom, you can do it without even trying. A few moments, so I'll share some history with you for a few seconds. If you look at the history of calculus, it was done through a guy called Leibniz and another guy called Isaac Newton, right? The guy, the apple dropped in his head, the gravity guy. And he allegedly, and I believe it's true, he sent a letter to Leibniz telling him all about this cool stuff that he just discovered and how he could use it to do the, for instance, Newton's the guy that figured out planets go around the sun in elliptical orbits, not circles, right? And he used calculus to do all of that. And he told it to Leibniz, and this is where the story differs. Newton said Leibniz stole his idea and published a paper all about it and got a lot of kudos for it. And if you can imagine, Newton was not very happy. Leibniz said when that letter arrived with all this stuff in it, he kind of panicked because he'd already figured out calculus himself. And he didn't want Newton to publish the book and get all the credit, right? Because, hey, that's my idea. I'm going to publish it first. Well, it's up to you. You can either believe Newton or you can believe the German Leibniz. And it's not like a German ever did anything bad, right? So you can choose. And that's us for today. Bye-bye, everybody. I'll hang about for homework. Remember to put your last name down for attendance. And tomorrow we'll start talking about the finals.